these are the problems that look like this in your algebra 2. It was 2 cosine x minus 1 equals 0, and you would solve it for either a general solution or within one revolution. Remember that?
Nope.
So you had 2 forms of it. It was a general solution or we'd say solve for x within one revolution or between the barriers of 0 and 2 pi. Okay. We would do it that way. General solutions were the ones where you guys always had a problem with. Within one revolution, you guys, it was easy. Okay? It was a lot less work. So if I'm looking at this problem where I want to solve 2 cosine x minus 1 equals 0, and I want to solve for x, you solve it just like you would any other algebra problem. First thing you're going to do is what? And then what?
Divide by
2.
So you add 1 divided by 2. We get cosine of x is 1/2. To get x all by its lonesome, then you'd have to inverse it. So you're basically asking yourself, what angle has a cosine of positive 1/2 within the full unit circle? Okay, we're going all the way around. All right? So the cosines. Oops. I can't even write today. Which one of those has the cosine of a half? Pi over 3. The 60-degree angle. So at 60 degrees, cosine is 1/2. What other quadrant is cosine positive then? You get there eventually. So you have 2 spots where you have a cosine of a half. Remember, you're using the 60 degrees or that pi over 3, basically radians. You're using that pi over 3 as your reference angle. So if you go up there, pi over 3, you go up pi over 3 from the whole, you're at 2 pi over 3. So your answers would have been x equals pi over 3 or 2 pi over 3. That would be if you're looking at it within one revolution. The general solution was the different one, where you had to tack on the pi however many times, how long it takes you to get back to that position. So if I'm looking at these 2 points, going from pi over 3 to 2 pi over 3, is that the same distance as going from 2 pi over 3 back to pi over 3? No. So what happens then is that every time I'm at a pi over 3, if I go around one full revolution, I'm back at pi over 3. Back at pi over 3. Back at pi over 3. Same thing with 2 pi over 3. So this is your solution within one revolution. And the other one would have been pi over 3 plus 2 pi n for the number of times you go around. Okay. And that 2 pi n revolution, it could be different. If they were opposite one another, especially with like tangents, they were first and thirds. It was always like a lot of times it was a pi revolution. It was pi over 4s, like all 4 of them was plus pi over 2 and so on.
So it's got always
Getting harassed by people. So what happens here again, if we're talking about a general solution, the general solution is when you start at the pi over 3, every time you get back around one full revolution, you're back at pi over 3. Same thing here. You go around, you're back at where you started. Every time you go around one revolution, you're back where you started. That's all it is.
So do that final time.
What's that?
So do that
That's all it means. That's it. All right. Depending upon how some of the problems are, though, sometimes you're going to have it where you're here and here for like a tangent problem. Sometimes tangents will be only pi apart. Yet from here to here is 180 degrees. Here to here is 180. So every time I oscillate 180 degrees, I'm back to a solution. So I'd say plus pi n, as opposed to going all the way around.
So it's either plus pi or plus 2 pi?
Plus pi plus 2 pi. It could be plus pi over 2. Pi over 2 happens when you have them at 45 degrees in all 4 quadrants. They're all equidistant from one another. They're pi over 2 away.
So it's either one of those three,
Yeah.
not anything else?
No. Okay. And as we get into this, you'll see how this stuff goes. And I know we've done this, or I know that you guys have seen it. I know you have done it. It's just a matter of getting back to it. If I'm not mistaken, though, I think the pre-calc book, still here's real fast since you're hiding your phone underneath it. Yeah, sometimes it'll say just find the solution, which means it's looking for that general solution, or it'll say find it within one revolution. So if you don't see that in a problem, that means you have to worry about that plus pi n, plus 2 pi n, plus pi, which one of those, okay? That's the only differences. Thanks. Let's try another one. Oh, we just, no. Might as well. 2 sine of x equals 1. Solve for x. What do you do?
Divide by 2.
Divide by 2. Good. What angle has a sine value
30.
of 1/2? 30 degrees. Pi over 6. So where is sine? Wait a second, did I screw that up and do cosine with the top 2 quadrants?
Yeah.
Oh, what the hell was I thinking? I'm sorry, it's down here.
So I was right.
Yeah, I just realized I did that. Because I was so used to doing the sine problem first. Wow. I didn't mean to. I just realized I did that. I didn't.
Okay, so how do we fix the problem then?
Okay.
Screwed it all.
So they're only
When I did this, I did the cosine of x. For some reason, I thought I was doing a sine problem. In my head, I was doing a sine problem because in my notes was to do a sine problem first. But for some reason, I wrote down cosine. So it was just a dumb mistake. So this should be, when we're cosine, you're positive here and here. So it was pi over 3, and then this point, as you come all the way around, would have been 5 pi over 3.
So it's pi over 2.
It's still going to be plus 2 pi n plus 2 pi n. For some reason, I thought I wrote down sine, and that wasn't a sine.
Wait, why is it still 2 pi?
Because in order for you to start at 5 pi over 3, how long does it take you to get back to 5 pi over 3?
Oh, so it doesn't matter like where the other one is?
The distance from here to here is not the same as the distance from here to here. That's all.
Oh, okay.
That's all it is.
Makes sense.
So I apologize. I honestly thought I was doing a sine problem. I don't know why I got that mixed up because I apparently can't read.
You're a math teacher.
I didn't say that there was reading involved. So it's supposed to be 5 pi. Anyway, so if we look at it in terms of sine, sine is positive 1 and 2. So this is your pi over 6. And what is it in the second quadrant in terms of radian? They're coming up, it would be at?
Pi over 6.
What's pi over 6 less than a whole?
5 pi. So,
Okay? You're just working them through like that.
and then, so it's still plus 2 and at the end.
2 pi n.
Yeah.
Okay? So your answers would be pi over 6 plus 2 pi n and 5 pi over 6 plus 2 pi n. Because those 2 points are not equidistant going from pi over 6, 5 pi over 6, and then back again. It's not the same distance. But wait, there's more. It slices, it dices. Sine of x plus root 2 equals negative sine of x.
Everybody gets.
Wait, since, is there gonna be trig identity tests?
Yeah, remember even with the equations, sometimes there's some trig identities.
So then does that mean that we're gonna get an algebra?
Yeah.
Like a new one, or we
Yeah.
just do something?
You can do
Did you
it.
say you guys were going back to
Yeah.
or is that each other?
I think in this one. So, again, you're back to an equation, variables on both sides. What do you do when you have variables on both sides of the equation? Pick on the little guy. Which one are you going to move? A positive one or a negative one?
Or negative.
So you add sine of x. Now you have 2 sine x plus root 2 is 0. No.
And then you divide by
What angle has the sine of negative root 2 over 2?
40.
So it's a 45-degree angle. Sine is negative in the 3rd and 4th quadrants.
Yes.
Pi over 4 reference angle, so that puts you at?
5 pi over 4 is 6 pi. 7 pi over 4.
Now, going from 5 pi over 4 to 7 pi over 4 is 90 degrees. Going all the way back around, it's more. So you can't, they're not equidistant from each other, so that means you have plus. Were you saying, does it matter which one you put down first?
Yeah.
No, not at all.
Wait, do you have to put both of them?
Yeah, because there's 2 angles.
Okay.
Root 2s, the root 2s and stuff like that. You agree that's going to be in 45.
Yeah.
So if you're in the 45s, that just means that your reference angle is pi over 4. So if I'm pi over 4 up, sine's both positive. If I'm pi over 4 down, that's when sine is negative. So down pi over 4 is a fourth less than a whole, or 2 wholes I should say. So that was the same as saying 8 pi over 4. Subtract 1 pi over 4 gives you the 7 pi over 4. Same deal over here, I add 1 to a whole and I get 5 pi over 4. You're always adding or subtracting off the x-axis. All right? Sure. So a lot of this stems from just solving equations, working through and solving them out. Three tangent squared x minus 1 is 0. Three tangent squared x minus 1 is 0. What do you do first?
Subtract or add.
Add 1 divided by 3.
Good. Add 1 divided by 3. How do you undo squaring?
Square root.
Now you're taking a square root over an equal sign, so what do you have to put on both sides?
Plus minus.
I should say on the other side. You gotta do plus minus. So you get tangent of x equals plus minus 1 over root 3. Because what's the square root of 1? 1. Do I need to rationalize this? No.
No.
Because I'm going to ask what angle has a tangent of 1, excuse me, plus minus 1 over the square root of 3. What triangle has the root 3's? The 30, 60, 90. Now, if I'm looking at tangent, I can make this full. But if I'm looking at, tangent then, which one of those is the opposite one, the adjacent root 3? The 30. If you want to rationalize because you think it's cool, go for it. But this is a case where rationalization doesn't make any sense because it doesn't matter for the rest of the problem. You know that your reference angle is going to be 30 degrees, pi over 6. Tangent, it's saying find all the angles with that has a tangent value plus or minus 1 over root 3. How many angles am I going to have then? 4 of them. I'm going to have all 4 reference angles of pi over 6.
Do you want us to draw this out?
Sometimes it's easier to see. Okay? If you're good without it, that's fine. Personally, I like to draw them out because I know I'm not going to miss something. And it's easier for me to add whether I'm adding or subtracting my reference angle off the quadrants. Okay? So pi over 6 in the first quadrant? Not necessarily. Pi over 6 up here, pi over 6 up here gives me what in the second quadrant?
5 pi over 6.
All right, so we start listing. We have pi over 6, 5 pi over 6. What's next?
7 pi over 6.
7 pi over 6, and 11 pi over 6. There are 4 angles that give me a plus minus 1 over root 3. Now, what Maddie was saying, hey, isn't that going to be the one where you have to add the pi over 2 each time? If I was to do that, that means to go from from 30 degrees to 150 to 210 to 330. That means from 30 to 150 is the same amount going from 150 to 210 as it is to here, as it is to here.
Oh, no, that's only for the 45.
Correct. So in this case, it doesn't work. But notice, if I go from 30 to 210, how far apart are they? It's half, it's pi, right? Same thing here, from 150 to 330 is still just pi away. So I don't need to write out all 4 of them plus 2 pi n. A more simplified version would be pi over 6 plus pi n and 5 pi over 6 plus pi n. Number of times you go around.
Oh.
Because no matter how many times you have n, you're always going to wind up on 5 pi over 6 or pi over 6 as far as the reference angles. So you'll have a plus or a minus value of tangent there. So what you're looking to do is figure out the most generic, general answer. This would be the most general here, as opposed to listing out all 4 of them. That's when you're talking about what we call that general solution. You're looking for how long does it take to get from each part. Is this 30 to 150 the same distance as 150 to 210? 210 to 330 is the same as 330 to this gap. These 2 gaps are the same. These are 2 the same. But if I go from here to here, it's the same as going from here to here. Same thing here. So an easier way of writing it out, instead of saying pi over 6 plus 2 pi n, 5 pi over 6 plus 2 pi n, 7 pi over 6, and so on, is to write it like this, and you're done. Okay? Does that make a little bit more sense? Now, if this problem said this, if it did, your answer would just be that, with no revolution.
But if we did all of them.
Well, it just means you're not reading the instructions. Oh, I thought you were not me. Okay. Stop screwing up. All right.
There's more.
All right. what do you do first?
Subtract the sine or cosine.
Divide by
You cry.
No, because then you eliminate a solution. Yes. Set aside equal to 0. Okay, set aside equal to 0. So we get cotangent x
Oh, this.
cosine squared x minus 2 cotangent x equal 0. Okay. Notice you have two terms. What do both those terms have in common? Cotangent. Factor it out. Do you have two terms equal to 0? Set them both equal to 0. The properties for solving polynomials work the same when the polynomials are trig. So you have two separate solutions to solve for. Cotangent of x equals 0, and cosine squared of x minus 2 is 0. We solve them out that way. Okay. So what angle gives you a cotangent of 0? Well, that means we have to remember what cotangent is. Oops. Cotangent is the inverse of tangent. Tangent is y over x, so cosine is, or cotangent is x over y.
Yeah.
Obviously, if it's going to equal 0, that means it's got to be on one of our quadrantals.
It's 0 and 1 and 0 and negative. So.
I want to make sure that I have x over y, where the y value is 1 or negative 1 and the x value is 0. Where does that happen? Maddie, where did it happen again?
90 and 270.
90 and 270, otherwise known as pi over 2 and 3 pi over 2. Are those 2 points equidistant from one another?
Yes.
Yeah, so what would be the general solution then? Pi over 2 plus pi n. Okay? We okay with that?
Do you have to write the other one?
No, because to get from the vertical axis to the, let's just say, the upper quadrantal and lower quadrantal, you're just adding pi back and forth. On the other one, you guys said add 2 and take the square root, right?
So it's root 2.
Ah, careful though. X equals the inverse cosine of plus or minus root 2. Because you have to take the square roots, you're going to have multiple angles. Okay. Where do you have cosines of root 2? Hold on here. Does that fall in anywhere for us? No. It doesn't fall anywhere for us. We don't have a triangle that gives us just a cosine of root 2. So sometimes you're going to get a problem where you just get plus or minus, or your cosine value is going to be plus or minus root 2, but you can't use a triangle to get there. We don't have a triangle to make that work. All right? We don't have that to work with. So right now, all we have is just pi over 2 plus pi n.
You just leave it.
Yeah. When we get to the ones, it'll actually, there's a way to show how it works. But in this case,
Just leave it?
yeah, because you can't solve it into a triangle. Okay? Now, if this was a 2 cosine x minus 2, well, that wouldn't work because it'd be add 2 divided by 2, you have square root of 1, so that wouldn't go. 4. Add 2 divided by 4, you get 1/2, and you have 1 over root 2. And things like that would work. Okay? So you got to watch some of these. Some of them don't drop to a triangle. You can't do it. Right. Here's the different style problem then. Notice how at the very tail end it says solve Sine squared minus sine minus 1 equals 0 on the interval 0 to 2 pi. It doesn't need that pi in. It doesn't need that times revolution stuff. You just solve for all the possible angles that can give you this value. That's it. All your different radian values that work. Less thinking involved. Now, I don't know if you guys remember the tricks sometimes when you're factoring with sine, or you're factoring with stuff that looks nasty. But I think we've done it a few times here now, that U substitution.
Yeah.
It just makes life easier. Just show it. I think some of you guys have done it in your quiz. It's a smart move.
That was me.
That's fine. Okay. So if I do that real quick, I get 2u squared minus u minus 1. What times what's negative 2? If you add together, you get negative 1. Negative 2 and 1. And you factor it by grouping. What do they have in common in the first set?
2u.
Next one, what do they have? 1. Are these the same? Good sign that you're doing something right. Those two are the same. Write it down. But when I go to write this down now and save myself another step, what did U stand for? Sine. Somebody's write sine of x.
So you have to put it back in.
Yeah.
Oh gosh, I didn't do
And now you're back at your two terms set equal to 0. So you set both of those equal to 0 and solve.
that. Should have done.
We have. We've done it. We've done it.
We did it.
We did. You might have been texting, so that's okay.
Oh. We get to all the time.
So you set both those terms equal to 0 and solve for x. Where is sine equal to 1?
First quadrant.
Pi over 2.
Where is it equal to 1? Pi over 2. Where is sine equal to negative 1/2?
In 7 pi over 6 and 11 pi over 6.
Oops, do this. We know it's a 30 degree, so it's pi over 6. What two quadrants is sine negative then?
3 and 4.
3 and 4. So like Maddie said, pi over 6 reference going down to the third quadrant gives me
7 pi over 6.
7 pi over 6.
11 pi over 6.
What?
Here's what I'm saying, what she said.
There you go. You don't have to worry about tacking on that pi in or any of that other stuff because they put that bracket here between 0 and 2 pi. They're just looking for the revolution within one revolution.
So then your answer would just be pi over 2, 7 pi over 6, and 11 pi over 6.
Yes. The answer is yes. Okay? This is the one where you have to switch them. Going from one Pythagorean or one identity to another. And there's a really easy trick to remember. I can't solve that right now because I have two different trig functions. I need one trig function to be able to factor. So usually what you're going to do is you're going to work with Pythagorean identities and you're going to try and put whatever squared term it is, you want to rewrite it in terms of the one that's not squared. So instead of using sine squared, I'm going to use cosine squared. The Pythagorean identity with sine squared and cosine squared was what? Sine squared plus cosine squared equals 1. So what does sine squared equal? substitute in?
Oh, I did this
And you substitute that in and redistribute. Yeah, it can be. Usually it's sine squared and cosine squared as they go through these. I mean, I think you might see a secant squared with a tangent and so, but it's usually one step. Now, when you go to distribute, I want you to see what happens. You get 2 minus 2 cosine squared plus 3 cosine minus 3 is 0. Combine your like terms, you get 2 minus 3 to get negative 1. Everybody okay with that? I don't know about you, but if you remember when we did factoring, we always wanted that first term to be positive. So let's just send everything to the other side, and all of a sudden the first term is positive.
And that changes it.
Yep, basically multiplying everything by negative 1. Both sides by negative 1. I just change the signs by adding everything over. It works the same way. Okay, it's the same thing as multiplying everything by negative 1. Now you have a factoring problem that's not so bad. What times what's positive 2 you add together to get negative 3? Negative 2, negative 1. You know what, I'm going to write it out with this U again just so you guys. Everybody okay? I just put U's in again? So you don't get lost in all the cosine and all that other stuff.
Wait.
And then I do another factor by group. When you have this third term negative, make sure you put it inside the parentheses so you remember the factor. So you have 2u. So you have 2 cosine of x minus 1. Let me just do one that had cosine of 1. Or will I have a sine? I'll get my sines and cosines mixed up again. Add 1 divided by 2. Where are your angles? Those two. Well, there's only one positive, so.
Oh, right. This one.
So what's the answer?
Cosine 1. No.
What angle has a cosine of 1? Zero. What angle has a cosine of 1/2? So pi over 3, cosine's positive 1, cosine's positive in 4. Yeah, sorry.
How that 0 was this? That you're trying to.
Oh.
You're trying to tell us like.
How many more of these are there?
I don't have any more words.
There's still a few more to go. This should get you a good start on the day one. I've got converting the quadratic, square. Yeah, we'll do this one tomorrow. The multiple angles we'll do tomorrow. and functions with multiples. And that, yeah. So we've got, I don't think you have to worry about that on day one stuff. Is day one you go what? Was it 3 through 24 every third?
3 through 4. Yeah, 3 through 42 multiples of 3.
Okay. 18, we'll talk about 18 tomorrow. I know that right off the bat, I can see that will be one. And it was 3 through 24 multiples of 3, is that it?
42.
42.
And 42 or through 42?
Through 42.
Okay. So I know 18 is going to be a problem. Yeah, we just don't have time to get through multiple ones. Yeah, if you get to the one where it's like a multiple angle one, or you have no idea what you're doing, it's probably okay because we haven't done an example yet. So, like I said, there's about 3 or 4 more examples to go through. We just don't have time to get through all of them today. I figured this is a good spot and we'll just go from here.
What are we doing the rest of the week?
Not this week, it'll be next week. It'll definitely be next week. Yeah, this week we're gonna go through, we'll finish out the 5-3 tomorrow. 5-4 is pretty quick. It's not, as you saw in the homework, there's not a lot of homework at that one. And then 5-5, Thursday, Friday.
It was as much as you